and he's still there today working with Emily Wisniewski. So lots of his work overlaps with lots of the work that we do here. I'm really excited to hear about you.
Thank you. So before we begin, I just wanted to acknowledge the Nunavut people who are the traditional owners of the land on which I work in Canberra, as well as the Wajik Noongar people who are the traditional owners here. I'm not sure if I pronounced that right, but I want to pay my respects to their elders past and present and extend that to any Aboriginal Torres Strait Islanders that are here today or listening online. So today I'm going to focus on sharpening our view of galaxies by trying to convince you that linking multi-wavelength data with these beautiful IFS data sets can tell us a lot about galaxy evolution. So the motivation behind doing this is that different wavelengths tell us different things about galaxies. In order to get a complete picture of sort of the baryonic cycle of galaxies, you need to bridge all of these data sets together. And this is a very nice visual example showing Andromeda at various wavelengths in broadband emission, but also in various line emission of gas. And you can see, like, spatially that the structures of these different components is very different. And as someone who studies dust, I always like to show this particular example, flipping back and forth between the optical image of Andromeda and the mid-infrared image showing the dust emission. And you can see that the regions that are the most strongly dust obscured are those that are strongest in dust emission. It's basically a kind of a mirror image. And so if you're only using one set of these data, you're sort of missing the complete picture of this galaxy. And of course, those are only two of the components of the galaxy. There's other components as well. And so you need to bridge all those together. And that's sort of schematically illustrated in this diagram, which looks very complicated. And the reason for that is because galaxies are composed of many different emitting components. The primary ones being stars, dust, and gas. And so you can see that visually. Stars dominate the bulk emission at UV to near infrared wavelengths. But some of that can be absorbed by dust, which is indicated by the shaded regions of this diagram. And that's re-emitted at infrared wavelengths, which dominates the bulk of the infrared emission. And you can see that gas emission is subdominant in broadband at all wavelengths. And so the way we trace this is actually through emission lines. And particularly, we usually use optical emission lines like H alpha or other series of lines. And the optical to trace ionized gas, which is what the integral field spectroscopy that I'm going to highlight today is doing. But we can also trace molecular gas through CO and atomic gas through H1 21 centimeter emission. And bringing all of those things together allows us to basically constrain the majority of the components of galaxies. So the first survey that I wanted to highlight is Typhoon. This is a completed survey of 44 galaxies that are all very local, large angular sized galaxies in the southern sky. If you're interested, the QR code here goes to the website that has like a full list of galaxies on it. But the fact that this is a southern sky survey is really ideal for linking it to ASCAP, because the vast majority of these galaxies will be observed with ASCAP, and because of their very large angular size, they'll basically all be resolved in the ASCAP data, which I'll highlight a little bit later. The nice thing is that it ranges over quite a bit in terms of like stellar mass of galaxies. So it encompasses things from dwarf galaxies all the way up to large spirals. So here's an example showing M83. The thing about Typhoon is it's not sort of a traditional IFU data set that you probably are familiar with, like MUSE or SAMI. And the reason for that is because it's constructed using long slit steps. So you can see that in this first panel here, this data set is constructed using 179 different slit steps across the face of this galaxy. So this is why it has such a giant field of view, is because it's using an 18 arc minute length slit that's just stepped across the face of the galaxy. But the main important bit is that the end product is still like an IFU data cube. So you get these panels here on the right are just showing the spectroscopy in different regions as highlighted here for this galaxy. And the wavelength coverage spans like lines going from O2 all the way out to S2. And this is a very like broad wavelength coverage, providing a lot of useful emission lines for characterizing the interstellar medium of these galaxies, like metallicity, ionization, and pressure, and things like that. The spatial resolution of the data is moderate for optical data, but because of the very close proximity of these galaxies, it corresponds to super high physical resolution. So anywhere from 5 to 150 parsecs per spaxel, which is pretty amazing. And the data, we are planning to release the data through Data Central in early, hopefully next year. But if you're interested in getting involved or before that, just get in touch with me. I'm happy to facilitate more people to work with this data. Yeah, and as I mentioned, the thing that makes Typhoon unique is its massive field of view. And so that's illustrated here in the second panel here. So this orange box is the Typhoon field of view for M83. And those other colored boxes are showing the field of view, for example, of SAMI or MUSE. And so the field of view is anywhere from like 100 to 1,000 times larger than these other instruments. And that's particularly useful for comparing to low resolution data sets like far infrared or H1 21 centimeter emission. And so even in those other data sets, which are typically, lower resolution, like 10 to 20 arcsecond resolution, you can still resolve this galaxy pretty well. And by combining all of these different, data sets together, the nice thing is that these galaxies are all super nearby things that have basically been observed by every facility. And so most of them have data at all these different wavelengths to work with. And so it's really ideal for trying to characterize the various baryonic components of galaxies in a spatially resolvable manner. And here's just another illustration comparing Typhoon to the FANGS survey, which some of you are probably familiar with. FANGS was a large program looking at very nearby galaxies by tiling MUSE across central parts of these galaxies, which is a very expensive process because it's field of view. But there was about a handful of galaxies that overlap between these samples. And so this is just a visual demonstration that Typhoon is covering much larger effective radii than what FANGS does. The FANGS data are much deeper because it's on an 8-meter telescope versus Typhoon was on a 2.5-meter telescope, which I don't think I mentioned before. But the data, it depends on what you want to do with the data. If you're interested more in studying, for example, the nature of the gas at higher effective radii, Typhoon would probably be a more ideal data set. The other thing that's unique is that Typhoon has 4 galaxies in the survey. So FANGS is a survey of primarily massive spiral galaxies. About a quarter of the sample, Typhoon is 4 galaxies. These are also the closest galaxies, like in proximity in the data set. And so they also have the highest physical resolution, which you can see sort of if you look at like the H alpha image of this galaxy, NGC 3109. So its distance corresponds to a spaxel being 10 parsecs in size. And you can see like individual H2 regions and sort of like outflow structures. And so it's a very interesting data set for characterizing, the ISM of these dwarf galaxies. So the remainder of the sample is primarily large spiral galaxies, similar to, for example, FANGS. But of course, these are much larger angular sized galaxies than what is typically in FANGS. And so comparing to things like H1 could be really interesting in particular. And then there's also some AGN and CFR galaxies in the sample as well. So what I showed here is only about half of the galaxies in the survey, 44 in total. So what I wanted to do next was just to highlight some of the multi-wavelength projects that we're starting to undertake with Typhoon. This is an initiative that I've started at ANU with several of the students and postdocs to try to link other people's projects into Typhoon. There's a lot of other papers that have been done using just the spectroscopic data itself, which you can see listed on the website if you're interested in those. But so, as was already mentioned before, my interest is in understanding dust and dust attenuation in galaxies. Typhoon is perfect for this because we can use the Balmer decrement, which is the ratio of H alpha to H beta as a proxy for the amount of dust in various regions of galaxies. This particular example that I show, 3521, is a slightly inclined galaxy, and you can see visually one side of the disk is being more attenuated by dust than the other side of the disk. This is actually really useful because we can compare the dustier side to the less dusty side to infer what the dust is doing to the spectral energy distribution, which is this figure that's shown on the right. So basically what this is showing is the SED binned in different amounts of dust attenuation, which is this tau like parameter, which is referred to as the Balmer optical depth. The blue one is the least attenuated regions, and the orange are the most attenuated regions. And you see that the SED looks redder for the more attenuated regions as you would expect. But what you can do is you can actually just invert this to get back out what the intrinsic dust attenuation curve is for this galaxy. And I'm hoping to do this for the various galaxies in the sample to understand how these things change with like metallicity, for example, or other properties of the galaxies. And actually, I'll just highlight here this little dip that you see here is the 2175 Angstrom absorption feature, which is a prominent absorption feature in the UV that I'll highlight in a project that I'm working on at the end of the talk. So another project work that's being undertaken is done by Hayden Park, who is a PhD student at ANU working with me to look at the gas to dust ratio as a function of metallicity in Typhoon galaxies. So there's a number of galaxies that have data from Herschel, which is really good for mapping dust emission, like dust mass in galaxies. And she's using the subset of galaxies that have that together with H1 and CO data to constrain molecular and atomic gas masses. This has never been done before in a spatially resolved manner. And she's finding that there are subtle differences between dust to gas mass ratios done globally versus locally in galaxies. Part of that is due to the filling factor of warm dust versus cold dust in galaxies, and how you constrain dust mass depends on that. But there's also quite a big difference in, for example, the dwarf galaxy Sextans A. But of course, you can see that there's a big gap here. And actually, we just submitted a Koala program, and I heard 20 minutes before this talk that was approved. So we'll have 13 nights to look at a whole bunch of dwarf galaxies that have Herschel data with Koala to basically fill in the region of the box parameter space that I showed here. So stay tuned for that. Chenwei Chen is another ANU PhD student who's interested in using Typhoon to study spiral arm theories. So in different theories of spiral arms, you expect different pattern speeds of the gas with respect to the stellar and ionized gas components of galaxies. So for example, parts of the galaxy might have faster gas rotation versus stars, and other parts, it's the opposite. And this is defined usually with a co-rotation radius where that transition happens. But in some spiral theories, you don't have that. And so what she's doing is using these data sets to look for azimuthal variations. So in regions where one pattern speed should be more or less, you can see if you expect enhancements with star formation rates or metallicities and things in one direction versus another. And Typhoon is really great for that because the structures of these galaxies are very well characterized, and we also extend to very high effective radii where you can very easily characterize where this co-rotation and radius is happening by looking at other tracers like CO for the dense gas. Antoine Marchal is a postdoc at ANU who is actually part of the gas cap survey. So his background is in doing multi-component fitting of H1 data to characterize the various phases of the H1 gas in the Milky Way. But he's actually adapting his code, which is called ROSA, to work on IFU data sets. He's calling that one Cairo. So it's a really fancy Gaussian decomposition code that fits the entire data queue simultaneously. It basically uses spatially coherent information. So like neighboring pixels are used to infer properties of neighboring pixels. And this is much more efficient at recovering low signal to noise data relative to traditional spaxel by spaxel fitting techniques. And so this is particularly powerful for Typhoon because there's a whole lot of empty space above and below each of our galaxies. And if we can apply this to recover the emission line to higher effective radii, it could be even more powerful with linking to H1 data, for example. And so that's actually part of a planned project being undertaken by Win, who's another ANU postdoc. So for example, M83 has this really beautiful VLA high spectral resolution H1 data that maps, way farther beyond the optical extent of this galaxy, which is sort of like this region here. And so we're hoping that we'll be able to apply Antoine's code to try and constrain ionized gas higher above and below sort of optical disk that, as you can see, basically this is the extent that we're limited to through the traditional fitting techniques, but we're hoping to extend that using this new algorithm. And the last project that I wanted to highlight is that we're working with the Possum team to try and link the polarization maps that we'll obtain for nearby galaxies. This is work that's going to be led by Jackie Ma and Amit Seta, who are also postdocs. In particular, trying to understand if there are links between the strength of polarization to things like the star formation rate in regions of galaxies, because these are thought to be mechanisms that might be the ways in which the magnetic fields are being driven and enhanced in these galaxies. And if they're not correlated, then that might suggest that it's actually other mechanisms that are driving those fields. And then, of course, there's other ASCAP surveys that are not, or that are being undertaken that I'm not really fully engaged with at the moment. But my hope is that we can do that with Wallaby in particular. So the first high resolution maps of nearby galaxies are now starting to be produced from the survey. So this is showing NGC 5068 in H1, moment 0 and moment 1 maps. And linking that with Typhoon, I think, is a really, really powerful new area of research that we could do. And if you're interested in any of this, just please get in touch with either me or Chandra if you want to work on that. Right, and so with that, I actually wanted to just shift gears into MagPi, which I think is a data set with which we could do very similar things to what we can currently do with Typhoon, but at higher redshift in the sort of near-term future. So some of you are probably already familiar with MagPi. There's two of the PIs are located here, so Kate and Claudia. It was an Australian-led ELT large program, 340 hours in total. I think this is the largest single-use program that's not a GTO program. And it's, impressive. The data are quite amazing, as I'll show in a second. So the goal of the survey was to study, or is to study, the drivers of galaxy transformation at a redshift of 0.3, which corresponds to 3 to 4 gig-years ago. In particular, the goal is to study galaxies across a range of environments to understand how much environment is affecting that transformation. And so the Muse coverage is actually slightly redder than other IFU data sets, but because the samples at redshift of 0.3, the data gets shifted such that you still cover the O2 to S2 wavelengths, which is the same wavelength range that was covered by Typhoon, for example. And so you, again, still have access to all these great emission lines to characterize the interstellar medium. This QR code links you to the MagPi survey website, and if you're interested in getting involved, there's a project submission page on that website, and anyone is welcome to join or pitch projects. So please feel free to do that if you're interested. This panel on the bottom is basically putting MagPi in the context of other large IFU surveys that you might be familiar with. So for example, SAMI and MANGA are these two boxes here. You can think of MagPi, this is showing this relative spatial resolution as a function of redshift or look back time. So things above that dashed line of 1 are basically resolved. So you get, multiple regions that are where you can characterize the properties of the ISM of those galaxies. And you can think of MagPi as sort of a SAMI or MANGA-like survey, but at a redshift of 0.3, which corresponds to 3 to 4 gig-years ago. And this is because it's using adaptive optics on the VLT. And this is essentially the best we'll be able to do until the ELTs come online. Although James Webb will probably provide subsamples of galaxies at higher redshift. But I think in terms of size, there won't be anything comparable to this for a while until the ELTs come online. So this is a gallery of 35 out of the 56 eventual fields that will be observed. So 42 have actually now been completed. And I think it's actually slightly more than that. But that's over 80% of the survey has been completed. So we're well underway into a lot of the science that we're hoping to do with the survey. This table on the bottom right just puts MagPi in context with respect to Muse Wide and Muse Hubble Deep Field, which are two GTO programs that were very large. You can see it sits in the middle tier at 4 hours per exposure relative to Muse Wide, which is only 1 hour per field. And The thing to note is that the survey was focused at this redshift of 0.3 crossing a range of environments. So that's what's shown here. The orange circles are galaxies at that redshift of 0.3. However, of course, you get a whole bunch of other extra galaxies that are just happen to be in that field of view. Some of which are below that redshift, but most of which are actually beyond that redshift. And that's illustrated in this panel in the bottom left, which is showing the distribution of galaxies that have robust spectroscopic redshifts, so 2 or more emission or absorption line features to characterize the redshift. And there are expected to be over 2,500 galaxies with robust spectroscopic redshifts, of which about 700 of those will be at the primary redshift of 0.3. So that's a lot of galaxies, to characterize and understand galaxy evolution with. And again, highlighting that those galaxies at 0.3 will span a range of environments from basically isolation to clusters. And I just wanted to highlight one field in particular and illustrate some of the nice emission line maps that we're getting from the data. So I'm actually the lead of the emission line working group for MAGPIE, also Typhoon. I don't think I mentioned that before. So I'm very familiar with producing all these emission line maps, or if you have any questions about things you might be able to do with these data sets, I'm probably a great person to ask about that. The thing we're actually in the middle of pursuing right now is multi-wavelength follow-up in order to try to do a lot of the things that I'm currently doing with Typhoon for MAGPIE in the future. We've actually already been successful with some of this. So I had an HST proposal approved last cycle, which I'll highlight in a little bit, where I put in a bid for a James Webb Large Treasury Program, and we're also submitting ALMA proposals as well. So we're very actively pursuing multi-wavelength data sets. There's also EMU radio data for these galaxies, and it might be possible to stack the galaxies to get H1 from DINGO, although this is maybe pushing the sensitivity of DINGO a bit much. But again, we'll have a lot of really great data for these galaxies to characterize galaxy evolution. I also just wanted to quickly highlight a project that's being done by honor student Amy working with me. His project was combining SAMI and MAGPIE to understand how much the relationship between dust in galaxies is changing with redshift over the sort of marginal redshift range that we have access to. So this panel on the bottom right is showing the Balmer optical depth parameter that I highlighted before. So larger values mean more dust as a function of things like metallicity, star formation rate, surface density, and stellar mass surface density. And you can see that there seem to be more marginal changes in these patterns. And this is important because if you want to have a way of correcting for dust in galaxies, when you don't have ideal ways of tracing the dust directly, like through spectroscopy, for example, you'll probably need to rely on types of scaling relations like this to do it. And so the hope is that this will serve as sort of low redshift baseline and then can be extended at higher redshifts in the future, most likely with like James Webb or Roman or Euclid, which will also get spectroscopy of high redshift galaxies. Right, and so with that, I wanted to just summarize again these two great data sets that I think have the potential to do a lot of great science to understand the interstellar medium and also the various phases of gas and stellar components of galaxies. Typhoon can do this very well for the local universe. MAGPIE has potential to do this at slightly higher redshifts. And I think in terms of their capabilities, there's nothing quite like them on the foreseeable horizon until we get like the ELTs. And with that, I wanted to switch gears and talk a little bit about some science that I've been doing. It wasn't listed in the abstract, and I apologize for that, but I wanted to actually show a little bit of science as well. So I've actually been doing a project looking at the link between the 2175 Angstrom absorption feature, which I highlighted a little bit before. It's the most prominent absorption feature in dust attenuation curves. And it's a potential link to polycyclic aromatic hydrocarbons, which are very small dust grains that are very easy to measure with James Webb. And so this project is linking data from SWIFT, which is a UV telescope, together with data from the FANGS survey, which is a great, amazing data set. So just to give a little bit of motivation, there was the slide I showed before was very similar to this, but this hopefully is simpler in its interpretation. It's basically just showing the spectral energy distribution of a star-forming galaxy, how it changes due to dust. So the underlying stellar population would have something similar to this blue curve in the absence of dust, but of course dust will absorb that light more preferentially at bluer wavelengths than at redder wavelengths. And all of that energy that's lost, basically the difference between the blue and the red curve over here, is being re-emitted in infrared wavelengths. And these interesting features that you see over here, these are the polycyclic aromatic hydrocarbons. So they're emission associated with very small molecules that are basically thought to be the smallest size dust grains. And the smallest dust grains are the ones that absorb the most at UV wavelengths. So these are thought to be the most likely carrier of this 2175 angstrom feature, which occurs over here in the ultraviolet. But the thing to note, or that I wanted to highlight here, is that we don't really understand this wavelength-dependent absorption of dust very well. And depending on how you treat it in correcting it for it, it affects your inferred physical properties of galaxies by large factors. And I list some values over there. In particular, something that's, I think, less well understood is that it also affects the ability to constrain photometric redshifts of galaxies. And this bump actually can also lead to large differences because it can be misinterpreted as a alignment break, for example. And this poses a major challenge for precision cosmology, where galaxies are used to basically measure the large-scale structure to infer cosmological parameters, such as what's being planned with Roman and Euclid, where they're going to require accuracies of greater than 5% to achieve their science goals. And I demonstrated in a paper a couple years ago that our current understanding of dust basically allows us to only reach 10% accuracy if you're dealing with it. I mean, not every galaxy has dust, and so this might be an overestimate, but it's definitely a problem. So we need to try to understand dust curves better. So how do we actually go about correcting for dust? There's basically 3 techniques. The first is that you can use this energy balance effect. So if you have infrared data, that's great. You can basically just take the amount of energy over here to figure out how much you lost over there. But this region of the spectrum is usually unavailable for the vast majority of galaxies, especially at high redshifts, where ALMA is basically the only facility that we can use right now to do that. And the other way you can do this is through spectroscopy. So using the Balmer decrement, or the ratio of H alpha to H beta, which is what I was alluding to before, that can be used to trace how much dust is in a region. But of course, not every galaxy will have spectroscopy either. And so the vast majority of methods used to correct for dust is just to make an assumption about how this absorption as a function of wavelength is occurring. And those are called dust attenuation curves. And I am shocked at the number of James Webb Redshift 10 galaxy papers that use dust attenuation curves that were derived at redshift 0 to infer all of their galaxy properties, which are almost certainly wrong, but it's still very widely done. And this is because we just don't have a great understanding of this at the moment. So this figure here is illustrating sort of our current understanding of dust attenuation curve evolution based on studies using this Balmer decrement technique. There are various ways you can do this, as I mentioned, but this one I think is the least prone to systematic issues. And what you can see from this figure, the colored lines are basically attenuation curves at different redshifts, is that there is a steepening in the UV slope as you go to higher redshifts. And this is probably linked to metallicity primarily. So if you look at the extinction curves, for example, of the Milky Way and SMC, those are shown as these gray lines. The SMC has a steeper curve, and that's attributed to the fact that it's lower metallicity. So there is a larger amount of smaller dust grains relative to larger dust grains, making ultraviolet absorb more preferentially than longer wavelengths. If you're interested, I just wanted to highlight there's a distinction used in the community between attenuation versus extinction, and this review paper is a great resource to get more details on that. It just comes down mainly to geometry. So extinction is measured along a line of sight, whereas attenuation is basically if you're looking at a region, you can have some stars that are foreground to dusk, some stars that are adjacent, and it makes it very complicated. The other thing that's very poorly understood is this 2175 angstrom absorption feature, which shows up as a peak here because this is basically showing the amount of attenuation as a function of wavelength. And it's, yeah, this is something that I think we can get a really detailed understanding of by using spatially resolved data like Typhoon or FANGS, which is what I'm using for this project in particular. So the PAWs have very long, or for a long time now, been thought as the main potential carrier of this 2175 angstrom feature. And actually, there was a really interesting paper earlier this year where they were able to reproduce this absorption feature in laboratory measurements using analogs of some kind. So this is showing inverted wavelengths, so more UV is to the right on this diagram, which is something that people working in extinction like to do. But basically this, I highlight here, this is the 2175 angstrom feature, and it matches very nicely in terms of its expected width and peak value. So this is very promising evidence that there is indeed a link, but this has basically not been observationally constrained or confirmed yet. And the reason for that is primarily the limitations of current facilities in trying to do this. The most important one probably being that we don't really have very good UV facilities to do this with. The probably, most ideal facility would be HST, but the HST filters are slightly too redward. And actually, they start at basically the 2175 angstrom feature, so you can't get a reference blue point using HST unless you go to higher redshift, which I'll point to as the whole focus of the HST program that I led with MagPi. But the other facility that you probably want to try to do this with is Galax, which is it did a very large sky survey, but it only had 2 filters. One of those filters lies right on top of this 2175 angstrom feature. So this blue curve is its far UV band, and then this dashed red curve is its near UV band, which is really wide. And using just those 2 filters, there's a degeneracy in how you fit the UV continuum versus what the effect of this bump is. And so Galax is really bad for trying to understand that, actually. And so fortunately, there is one UV facility that can do this right now, which is Swift. But it's actually primarily a transient facility, and it wasn't designed to do this. And working with the data is very complicated. I don't know if anyone's ever tried using Swift data, but it's a nightmare. But I fortunately met Marjorie DeClure, who developed a pipeline, which I'll highlight in a second, that deals with all of this. So it's now the realm of possibilities to do this. And it's nice because it has 3 filters, which are the orange, green, and purple filters in this panel here. So there's one on the blue side, one on the red side, and then one that's right in the middle. You'll notice that the curves on the blue and red side both overlap slightly with the bump, but it's actually sort of symmetric, so the effects isn't too important in actually characterizing the amplitude of the bump. And Marjorie actually tried to use Swift together with Spitzer to characterize this sort of for the first time, I think. And this was the result. And you can see that there's no correlation. And most of that, I think, is due to the observational limitations. And so James Webb has since come along, which is a huge, amazing improvement over Spitzer for this reason that I showed here. So this is NGC 628. The left is the Spitzer data, which was what Marjorie used for her project that was actually on this particular galaxy. And the right is the James Webb data, which is an order of magnitude higher spatial resolution. But the other thing is that James Webb has way more mid-infrared filters that are better for characterizing those PAW features in the mid-infrared. They were basically designed for that specific purpose. So the data set that I'm using for this project is the FANGS James Webb Cycle 1 Treasury Program. It was basically getting James Webb data for the FANGS Muse program. So all of these galaxies also have data from Muse to characterize the or that obtain optical spectroscopy, which is important because I can use that to get that Balmer decrement measurement to constrain the amount of dust in given regions. So the thing to note here is that the FANGS sample is, as I mentioned before, they're all primarily massive spiral galaxies above a stellar mass of log 9.5. And this actually means that they don't probe a very wide range of metallicities. They're more or less all around like solar metallicity. But they're still great because we can use it to test this, correlation between 2175 Angstrom feature and pause. And so the way I'm doing that is by combining or obtaining basically all the galaxies in FANGS that have SWIFT data. So when SWIFT isn't doing its transient follow-ups of supernovae and gamma reverse, it's actually has filler programs where it just observes nearby galaxies that might have a supernova go off in them in the future because they need a baseline with which to do all their transient science. And it turns out that 15 out of the 19 galaxies have data. Not all of those data are very high quality. Actually, only about 8 of them are sufficient for this analysis. But I would recommend, if you're interested in using SWIFT data, there's this great code called dress code, which is relatively painless to use to get these beautiful maps. So this is a 3-color composite image from the SWIFT data for NGC 4321. And yeah, the data are quite deep. Actually, for the most part, most of them, like when they look at these nearby galaxies, they're deeper than what Galax provides. And so it's really powerful for using or getting the UV data. And then these are showing the footprints of the MIRI, which is the mid-infrared instrument on James Webb. And then this is basically the MUSE footprint showing H alpha. So the region that I'm going to be using for my analysis are basically the regions where these 3 data sets overlap. And the 2 main parameters of interest that I'm measuring are this bump strength, which I infer based on these 3 SWIFT filters. So this is an entirely empirical measurement. I'm not making any assumptions about like the shape of the bump. What I'm doing is basically fitting a power log to the off feature filters because you expect the UV continuum to have a power law shape, and then finding out what the expected value in the median band filter would be, which is this orange point, and then comparing it to what's actually observed. And you can see that there's quite a big offset in this case. So the strength of the bump is pretty well observed in a lot of the regions of these galaxies. And the second parameter is this PA abundance, or the amount of PAs relative to larger dust grains. So the way that's measured is using 2 filters that were specifically designed to characterize the 7.7 and 11.3 micron features, which are the 2 strongest mid-infrared features. And they're normalized with respect to a dust continuum filter, which is measured at 21 microns. So this ratio represents basically the amount of these small PA grains versus larger grains. And so this is showing the maps for the galaxy that I showed you before, NGC 4321, but we basically find the same trend for all of the galaxies where we have good SWIFT data. So I'm just going to show this one as an example, and then I'll highlight the trends combining all the galaxies at the end. So the first panel is showing the bump strength normalized with respect to the amount of reddening, because you expect that the strength of that absorption feature will scale with basically how much total reddening that you have. And you need to normalize by that factor in order to understand the intrinsic strength of the bump. The second panel is the PA abundance. The third panel is specific star formation rate density. And the fourth panel is metallicity. And you can already, just by eye, sort of start to see that there are some correlations here. And the first, of course, one that I was most interested in studying was that there was a correlation between the 2175 Angstrom feature and PAs, and there does seem to be a moderate correlation. It's not super strong, but this is the first time I think it's ever been seen that there is a correlation. And it's consistent across all the galaxies that we have really good SWIFT data for. The thing that I think is probably, oh, sorry, I just also want to highlight that this mean strength or median strength of the bump in the galaxies is about 20% of the Milky Way. The reason it's lower is because when you have attenuation, you include effects of scattering, and that basically will always add blue light back into your line of sight, and that causes you to recover some of that absorption, basically. The thing that's probably more interesting is that there's a really strong anti-correlation with the star formation rate surface density, which is that third panel there. You can see it basically looks like a mirror image of the bump, the 2175 angstrom feature and the PA abundance. And this is most likely indicating that these small dust grains are being easily destroyed by ionizing photons from the star formation. And so I think this is the most promising metric with which to characterize presence or absence of the bump when you're trying to characterize the dust curve. Now you might think that there's some circularity there, like you need to get the dust to get the star formation rate, but the sort of lucky thing is that this 2175 angstrom feature is basically negligible total energy loss, and so it's not going to affect the star formation rate. So you have to make some assumptions about the attenuation curve shape, but it should be independent of the bump itself. Anyway, that's the hope. Hasn't really been tested very well yet, but the other thing that's very interesting is that there's essentially no correlation with metallicity. But again, part of this is, I think, due to the fact that FANGS is probing relatively metal-rich galaxies. I mean, you can see here, this is probing about 0.15 dex in metallicity, which is a really tiny range of metallicity. And so actually, that was the whole point of this awesome HST MAGPIE program that I was able to get approved last cycle. So we're getting 4-band HST UV imaging of the MAGPIE, some of the MAGPIE fields. So you actually just shift out to 0.3 in redshift, then the bluest HST filter is actually blueward of the feature again. And so you can use HST, which has amazing spatial resolution, to look at this in a spatially resolved manner for these redshift 0.3 galaxies in basically a similar way that I'm trying to do with the FANGS data now. But the MAGPIE samples probes a much larger range in metallicity than the FANGS data set does. And so hopefully I'll be able to examine how much metallicity is affecting the strength of this bump. And then if we get the James Webb data, we could then look at the pods and see if there's a link with metallicity in pods in the same way as well. So a lot of really fruitful, like, future research that can be done with these data if we get the programs approved. The other thing I just wanted to highlight is that there's a lot of other really great science that can be done from this HST UV data. So the depths are quite moderate because, again, these are 0.3 redshift galaxies, so you don't need to go that deep to see them pretty well. And basically all of the early type galaxies in the MAGPIE fields will be detected in ultraviolet. So if you're interested in characterizing like low scale star formation rates in like red and dead galaxies, it could be really interesting. It's also will be useful for characterizing Lyman alpha and Lyman continuum, which I didn't mention before, but they're of order 1,000 Lyman alpha emitters that are detected in the MAGPIE data. And we can sort of combine all of these filters together to put a constraint on the amount of Lyman continuum emission in those galaxies. Right, and so with that, I just wanted to wrap up. And this is now showing the 8 galaxies where we have good SWIFT data from the FANGS data set. Showing on the left is the bump versus pause. And then the 2 panels on the right are the trends with the star formation rate surface density. So these are what I think will be perhaps useful for characterizing when the bump is present in attenuation curves. And I'm hoping that with the new HST program that which will be starting in I think May of next year, we'll be able to try to extend this to understand over a wider metallicity range how these things are varying, or if there's in fact any evolution in redshift in these trends. Actually, and that I just wanted to advertise this 3D view of galaxies seminar series, which Luca is also involved in. Hopefully everyone here is on the mailing list, but if you're not, this is a monthly seminar series that we run where we're trying to bring together lots of people that are interested in bridging multi-wavelength data And so this QR code here will bring you to the Google Doc where you can sign up for the mailing list if you're interested. With that, I'm happy to take any questions.
So, questions from students first. Or for 10 seconds.
Very specific thing, but you said that when you had those 3 bands and the bump in the middle, that having the 2 bands cross over into the bump wasn't a big deal because they sort of cancel each other out. But how do they cancel each other out? Like, wouldn't they both now be a little further down and your bump's smaller than it actually is?
Yes, probably. So I haven't tested, that's sort of on my next on my to-do list, but probably there's a systematic offset in my 8 bump, basically parameterization. So it might be stronger than I'm actually measuring it to be, but the trends I think should be robust. Actually, 2 days ago or 3 days ago, there was a release of AstroSat data, which is UV data from an Indian facility. It's also very complicated to work with, but hopefully these produced data. A lot of those actually, because it was the FANGS data set, so I can use filters that are much more blueward and redward, where it should be independent to basically establish what this effect is.
The student questions are welcome to the room. This is better.
Thanks, Andrew. This is all great stuff. Really exciting. Can you go back to you had a slide about one of your students where you look at the optical depth as a function of redshift, that one.
Yep.
So what's going on there? So say at fixed metallicity, you have higher optical depth at higher redshift. Is this because you're making more dust, or is it a geometry effect? Are things a bit more compact and you have your lower column? Have you tried to look at that?
No, that's a great question. So I'm not sure of the specific reason. My intuition for seeing this result, the first thing I thought of was that it could be a result of there being more gas as a function of redshift. So if you have more gas, you are able to make dust more efficiently because of shielding. Mm-hmm. And so you might expect that for a given metallicity, if you just have more gas, you can make more dust at that same metallicity. If that makes sense.
Right.
But it could be geometry as well. That's something I don't think we can characterize, or it'd be very complicated to rule that out.
Right. And you don't have infrared data for this data set, right? You don't have Herschel Herschel wouldn't have a resolution. Because the missing piece here is the dust mass, isn't it?
Yeah, I mean, the hope is that we would get the MURI data, but that would only provide us with small dust properties, but it could still provide some interesting information. Yeah, for sure.
So much work. Wonderful, Andrew. It always highlights how ignorant I'm about dust, which is great. That evolution in the dust attenuation curves, the fact that you link that to potentially being metallicity in the early universe being different. Do we see that in actual metallicity variation in the local universe as well, that same variation in the dust curves?
Yeah, so the problem is we actually, most of the surveys where we have this are able to study. So actually this was that figure that I showed. That purple curve that I showed there, that was a study that I did during my PhD, trying to separate the Sloan Digital Sky Survey galaxies across various properties. And it turned out it didn't seem to change their effective attenuation curves all that much. But again, all of those galaxies are basically large spiral galaxies that are higher metallicity. So I hope is that with, for example, Typhoon, this project firm trying to study the dust attenuation curve on sort of individual galaxy bases. I've only done this for a couple of the larger galaxies. I actually haven't tried it yet with dwarfs. The problem also is that for dwarf galaxies, there's typically less dust. And so it's just intrinsically more difficult to constrain what the attenuation curve is for those galaxies. And so I'm not sure if we'll be able to have a clear understanding of this until it could be that once we have like blue war or whatever the current incarnation of the next UV space facility is. Because once we have an 8-meter class UV facility, we also basically be able to get extinction curve measurements of galaxies in the, like local volume. Basically, every galaxy in the local volume, we'll be able to resolve individual stars and characterize the dust extinction that way. And I think that would probably be the best way of understanding that.
Thanks. And quick question. First, your Swift. One of the issues with Swift is that the filter set is awful already, up to 4,000 or 5,000. I'm curious, how do you correct for it?
Sorry, there's a
red leak
Oh.
in the filters. How do you correct for it?
That's a great question. I don't think I am. So maybe
Okay.
that is a
Because
problem
it
that
would be
we need to look
interesting,
into.
but even now that there is also the Astrosat that you mentioned, because one of the challenges with Swift to do this kind of stuff is always because it's small in percent, but since it covers a huge range of wavelength, then you don't know whether you're detecting UV light or ultraviolet.
Okay, I will look into that.
That would be interesting. And then related to this, I mean, it's always a problem because everybody uses a different method because we don't have spectroscopy. And so there are hidden assumptions in every kind of color approach. For Magpie, have you thought of using a shooter? You should be able to get UV rest frame spectra, and then you have a spectrum. You don't have to play anything with broadband, narrowband, and making assumptions.
No, I have not thought of that. I think the problem would be we would limit it to a much smaller sample.
Sure.
Which
But you could test a technique that then you can apply to.
that's true. Yeah.
So going back to Xi Jinping's work with the dust to gas ratio, when we've done this before, we've also tried to account for the alpha CO variation. Now, with typhoon, maybe it doesn't matter as much because you're going much further afield. But are you accounting for that alpha CO variation as well?
Yeah, so I only showed the one where it's the fixed Milky Way value, but we are also using or make versions of these plots with metallicity dependent alpha COs. And actually, it doesn't seem to change the general trends. The more important factor is actually the metallicity indicator, because that shifts everything all over the place, left and right. But we're trying to adopt like the same one that was used for the reference line that like we're comparing to, so it should be consistent in that respect.
Another question. One thing that you talked about is bound decament. You haven't mentioned the other ones, right? Because you can use multiple hydrogen lines to trace the extinction curve across the gaps, right? So whether it be just H gamma, H delta, things like this,
Yeah.
or even probing down to the Paschen lines, things like that.
Yeah. So ideally, the wider the range of the lines you're using, the better your lever in understanding the dust. So actually, using Balmer series, H alpha, H beta is sort of the best. I mean, the other problem is the intrinsic flux of the lines gets weaker as you go to the higher order series. So comparing lines like H beta to H delta, H gamma, those lines are getting progressively closer in wavelength to each other, and so you don't get very much of a lever in the reddening. And so their intrinsic flux uncertainties tend to dominate with respect to that. So that's the problem with using the higher order news, like the Balmer series lines news data. Although I use the Balmer decrement as sort of the term, but I'm also using the other higher order lines as well if they're available in that measurement. Actually, so using these different Balmer lines allows you to actually characterize the underlying extinction curve of the galaxy. If you believe that the ionized gas suffers more from foreground extinction than the stars do. The stars are generally distributed regularly with respect to dust, but star forming regions are embedded in dense parts of galaxies. And so most of the obscuration is coming from outside of that region. And so there's actually been a few interesting studies where they've tied together like Balmer, Paschen, bracket series lines to characterize the underlying extinction curves of distant galaxies. But that's really expensive to do because you need to get the spectroscopy of those different.
Well, if there are no further questions, can we please thank Andrew again for